Good morning. In this talk, we'll examine the VeeR EH1 processor's microarchitecture. The VeeR processor family, originally called Swerve, was developed by Western Digital. They're now called VeeR and hosted on the Chips Alliance website. It's the same processor, just with different names. You can get the full EH1 processor for free on this site. These figures show the three processors in the EH1, EH2, and EL2 family. The EL2 is the lowest performing, with less power use and a 4-stage pipeline. The EH2 is a 9-stage multi-threading chip, and the EH1 we'll use has 9 stages. This table shows the main features of these three processors. The EH1 is a 32-bit RVfpga architecture processor that includes the base instruction set RVfpV with C and M extensions, C for compressed instructions, M for integer multiplication and division instructions, and implements numerous advanced microarchitectural techniques that we'll explain both theoretically and practically in this lab. The processor has a deep 9-stage pipeline, starting with 2 fetch stages, instruction alignment, decoding, 3 execution stages, and finally commit and write back. It includes 5 data paths, 2 integer, 1 load store, 1 multiplication, and 1 division. It has 2-way superscalar execution and supports multi-cycle operations. For example, multiplication takes 3 cycles. All instructions pass through the 9 pipeline stages with various forwarding paths, some of which we'll analyze in this lab's examples. It allows 2 branch predictors, a basic one that always predicts branches as not taken, and a share predictor. It has an instruction cache but no data cache, and a configurable scratch pad for both data and instructions, which can be disabled or enabled with various sizes. It supports misaligned stores and loads, non-blocking loads and divisions, and includes a technique called secondary ALUs, which we'll explore later. The EH1 processor includes RVfpV extensions, the C extension for 16-bit compressed instructions, allowing more compact code, and the M extension for integer division and multiplication. As mentioned earlier, the VeeR EH1 is a 9-stage pipeline processor. In this figure, we can see a basic overview of these 9 stages. It starts with 2 instruction fetch stages, an alignment stage, and an instruction decode stage. Execution is split into 3 stages, and finally commit and write back, where results are written. This figure shows the EH1 microarchitecture in much more detail. We'll explain each stage later. This overview is meant to show the processor globally, with 9 stages separated by pipeline registers. As we mentioned, the EH1 is a superscalar processor. The EH1 can execute up to 2 instructions per cycle, requiring nearly double the resources. In the alignment stage shown here, 2 instructions are selected per cycle. These instructions move to the decoding stage, where control signals are generated and sent to the appropriate data paths. For example, with two integer instructions like add and sub, each goes through one of the blue integer paths, 0 pip and 1 pip. With a load and an add, load takes the green path while add uses one of the integer paths. EH1 also supports multi-cycle instruction execution. Integer instructions take one cycle, with ALU results in the first cycle, while other instructions and paths require more cycles. Specifically, loads and stores need 3 cycles: address calculation, memory access, and data alignment. Multiplication is also pipelined in 3 stages, while division isn't pipelined and may take up to 34 cycles. In this case, the pipeline completely halts until the division result is obtained. Regarding memory hierarchy, EH1 has an instruction cache for instructions that retrieves information in one cycle. It can include an instruction scratchpad, though in our setup it's disabled by default. There's also external memory in this range requiring multiple cycles, accessed via the RAM Lite controller. For data, we don't have a data cache, but we will have it enabled. The data scratchpad allows data retrieval in one cycle and operates within this range. Then there's also the main memory we described earlier. Now let's analyze the 9 stages of the pipeline. This set of slides first shows detailed images of the 9 stages, divided into the first 3, and then the last 6, followed by a detailed description of each stage. In our case, we'll describe each stage using the figures. In the first stage, FC1, the address is generated and sent to both the instruction cache and RAM controller. In FC2, these memories are read. If the instruction cache hits, data is available in one cycle, but a miss means fetching from external memory, causing more cycles and pipeline stalls. Note that each access fetches 128 bits, equal to 4 instructions, excluding compressed ones. These 4 instructions are stored in one of 3 available buffers for the next stage. The alignment stage selects 2 instructions from these buffers for each of the 2 ways. We'll call the first way 0 and the second way 1. Memory access isn't needed every cycle, as each fetch brings 4 instructions, but only 2 are used per cycle. Thus, memory access is only required every other cycle. The 2 selected instructions in alignment propagate to decoding via instruction registers. These instructions are decoded, generating control signals for each, which propagate through the pipeline alongside the instructions and must be assigned to their corresponding data paths. For example, an add goes through an integer path, I0 or I1 in blue, while multiplication uses the orange path. Note that operands are read from the register bank, but can also come from forwarding paths of later stages, using these multiplexers and others not shown in the figure for simplicity. Next, instruction execution occurs, which as mentioned is divided into 3 stages. Each path will be different. The blue integer path has an ALU in the first stage, with minimal work in the second and third stages. The multiplier is divided into 3 stages, each performing a specific multiplication task. The load store path calculates the effective address, accesses memory, and aligns and combines data in its 3 stages. Note that a 3-to-1 multiplexer at the end of the third stage selects data from one of the paths. The commit stage selects from 3 paths, and writeback provides the result to the register file for writing if needed. Next, we'll explain how the H1 processor manages various risks in structural data and control programs. To provide a comprehensive understanding, we'll offer both theoretical and practical explanations of the simulator, using a program that evaluates various risk scenarios we'll analyze. This is the program we'll use. It's structured in 4 columns. After initializing memory and registers, it enters a loop where each risk situation we'll study is highlighted in red. Note the control instruction and 0T4T5 and at the loop's end. It halts the simulator. We'll execute up to this point, then continue to the second iteration, pausing at each analyzed situation. In the virtual machine, we'll open Visual Studio Code and Platform I/O, then load the RVfpga pipeline project. We'll replace the existing code in the assembly file with our example code, which we have here, and save it. From Platform I/O, we'll launch the RVfpga Bitbot pipeline simulator, which compiles the program and opens the simulation window. Clicking this button stops the simulator when the AND 0T4T5 instruction reaches decoding. Continuing execution brings us to the second iteration, starting with a multiplication. First, let's analyze structural hazards. A structural hazard occurs when 2 instructions try to access the same resource. In EH1, various situations like this can arise. For instance, when 2 multiplications reach the decode stage in the same cycle, since we only have 1 multiplier, only one can proceed while the other must wait. A structural hazard also occurs when 2 memory access instructions reach the decode stage in the same cycle. For the same reason as before, since we only have 1 path to execute these instructions, the second one must wait. Other similar conflicts exist, but won't be covered in this course. For example, in the first case with 2 multiplications reaching decoding, we'll insert a bubble in the second path, and the second multiply instruction will wait in decoding. Since the multiplier is pipelined when the first instruction moves to x2 for execution, the second can enter the first multiplication stage in M1, so we only lose one execution cycle. The first scenario shown in the example illustrates this exact situation, where two independent multiplications are consecutive, but both try to access the single multiplier unit, forcing the second to pause. If we observe this program's behavior in the simulator, we see that only the first multiplication can progress, and we must insert a bubble in the second path. The first multiplication will enter M1, while the second waits in decoding next cycle. The first multiplication advances to M2, and the second enters M1. The following cycle, the first multiplication gets its result of 8, and the next cycle, the second gets its result of 4. Now let's examine data hazards. There are various types of data hazards, particularly read after write hazards, which can cause issues, while war and wow hazards don't pose problems in this processor due to its structure. As mentioned, there are different raw hazards. For instance, two dependent arithmetic logic instructions create such a hazard, resolved later by forwarding. Or a multi-cycle instruction whose result affects a later instruction may require a processor stall before forwarding. Now, we'll analyze several of these potential situations. Let's start with a scenario where we have two closely placed arithmetic logic instructions. If these instructions are consecutive, with nothing between them, they can't run in parallel, as the second relies on a result being generated in the same cycle. So we need to introduce a bubble. However, if they're close but have an independent instruction between them, forwarding can resolve the conflict without stopping. This slide shows the 10 forwarding paths that can be used. 5 of these come from the same route, from the EX1 stage to the write-back stage. For instance, from X1, there's a path to the decode stage via this 10-to-1 multiplexer as a possible second operand. Note that the 5 paths from the opposite route are only shown by their signal names. Just like this 10-to-1 multiplexer, there'll be an analogous one for the first operand. This slide shows an example with an ADD instruction calculating a result in T4, an independent instruction, then an ADD instruction using T4 computed by the first ADD. In the processor, we'll have the first ADD in X1 stage while decoding the second ADD. As seen, the result from the first is forwarded to the second instruction's operand. This 3-to-1 mux will select the correct data from forwarding logic, not the register bank. Returning to our example, we now have 2 consecutive ADD instructions. In the simulation during this cycle, the first ADD instruction is in the decode stage. As we can see, a bubble must be introduced in the second pipeline because the next instruction depends on the result from the first one and can't be executed in parallel. Advancing one cycle, we see the second ADD instruction entering decode and the first moving to X. At this stage, the first ADD calculates its result 4 in the ALU, which is forwarded to the next ADD instruction. As shown, the second input gets a 4 via bypass, while the first comes directly from the register file. Moving forward another cycle, the second ADD progresses to X1, where it correctly calculates the sum. It might be useful to try locating some of these multiplexers in the Verilog code. Specifically, we'll try to find the 10-to-1 multiplexer. To do this, we navigate through the file hierarchy of the RVfpga package, entering RVfpga EH1, RVfpga src, which contains the shock sources, swerve-off shock, swerve-off1 core complex, which contains the core A1, and as we see here, we have several directories, many matching the stages, for example dec for decoding, xu for execution, or ifu for fetch. The swerve file instantiates each module, including dec, the decode stage, which in turn instantiates several modules, including decode control. Well, within this module, dec decode control, we can find the 10-to-1 multiplexer output. The multiplexer output. And we see that this output, it's assigned via a 10-to-1 multiplexer, with inputs matching those shown in this figure. A similar situation occurs when an arithmetic logic instruction is near a dependent instruction of another type. As I mentioned, the handling is similar. If instructions are consecutive, we need to insert a bubble. For example, here we have an add followed by a BNA, which depends on the sum's result, T. We need to insert a bubble, so this result can then be sent via forwarding through one of the previous paths. In this case, we have a sum that generates T3 and a store that uses T3 to calculate its effective address with an independent instruction in between, so we can forward the data without needing to stop. Another slightly different data hazard occurs when we have a store instruction where the data to be written to memory is calculated by a previous arithmetic logical or load instruction. Here's an example. Note that this addition calculates the result in T3, which we then need to store in memory using this store instruction, and both instructions are consecutive. Unlike what we explained earlier, it's not necessary to introduce a store. The reason is that the store needs the data in the second execution stage, not the first. So the processor has an additional forwarding path between the I0 path and the LS path, which provides the integer instruction's result to the store instruction if there's a dependency. Well, returning to our example, at this point we have exactly that situation. First, in T0, we're storing the address where the data is located. We want to write to memory, then we have an add that calculates the result in T4, stores the result in T4, and a store that saves T4 to this memory address. On the simulator, we can see how the two instructions can progress in parallel. The add calculates its result this cycle, while the store needs that value next cycle. This differs from a load followed by a store with dependent data, T3 in this case. The processor has a new path from the third stage's output to the second stage. So when load aligns and combines data, it's forwarded to the dependent store. Note that a stall is needed if these instructions are consecutive. And of course, we illustrate this situation in the example at this point. If we look at the simulator, we see the load executes right after the store, just needing a bubble in this cycle. Moving on, the load in DC3 gets its result, which the store needs at this stage to write to memory. Now let's look at multi-cycle instructions. Here's a multi-cycle instruction followed by a dependent arithmetic logic instruction. Since the multi-cycle instruction needs several cycles to get its result, the dependent instruction must wait until the result is ready, only then receiving it via forwarding. Notice that the paths used are the same as we explained earlier, namely these here, except these two paths won't be used, as the multi-cycle operation's result isn't ready yet. The multi-cycle operation's result isn't available until the third execution stage. Revisiting our example, we see a situation where a multiplication result is used by the next instruction in T. In the simulator, the multiply instruction progresses through M1, M2, and M3 stages, obtaining the result in M3. The processor introduces bubbles in the two cycles after multiplication, as the dependent instruction can't progress. In this cycle, the add instruction receives the multiplication result of 4 via bypass as its second operand. The first operand is fetched directly from the register file. Thus, the add instruction will correctly calculate its result using data from the register file and bypass. VeeR EH1 offers a solution for multi-cycle operation dependencies using an arithmetic logic instruction. It introduces an additional ALU, one per path, in the commit stage. So when an arithmetic logic instruction depends on a previous multi-cycle operation, the ALU operation is recalculated in the commit stage using the correct operands, which are now available. In our example, we can simulate this. The secondary ALU is configurable in EH1, and in our program we disabled it using these two initial instructions. We'll study these instructions later to see how to configure processor structures, but to enable the secondary ALU, we just need to change this 8 to a 0. Let's stop the simulation. And we launch it again now with the secondary ALU enabled. We'll run up to where we were, at the dependency between the multi-cycle operation and the arithmetic logic instruction. Now we see it's no longer necessary to introduce bubbles, as we have an extra ALU in the commit stage to recalculate the sum. Note that this sum result is currently incorrect, because it's operating on incorrect data. However, when we reach the x3 stage, the multiplication result is 4, and in the next cycle we'll see the sum change. At this point it's 0, but in the next cycle it becomes 6, which is 4 plus 2, with 4 being the multiplication result. Lastly, we'll look at a case with a load followed by multiplication. Here we have a multi-cycle instruction, so we might expect that multiplication can't start until 3 cycles after the load, creating 2 bubbles between them. However, in the processor we find that the first stage of the multiplier is very brief, allowing us to resolve the dependency with a new forwarding path from load's stage 3 end to the multiplier's stage 1. So, when the load aligns the data, it sends it to the multiplier stage 1, which does the first task and arrives in time to get the result of that first task and store it in the pipeline registers. In our example, we see this: a load then a multiply, where the first operand depends on the load data. And if we look at this simulator, we can see that indeed. What we discussed happens. We only need one stall cycle between the load and the multiplication that depends on the data loaded. The multiplication will receive the data from the load through forwarding and calculate the result correctly. To wrap up data hazards, let's briefly discuss the case of division. As we said, the divider is very slow and can't be pipelined, so the solution is to completely stop the processor until the division result is ready. At that point, if needed, it forwards to dependent instructions. Otherwise, execution simply continues. To finish our analysis of hazards, we'll briefly look at control hazards. These occur due to branch instructions, and processors typically include a branch predictor to guess the execution path. If the prediction is correct, no cycle is lost. If the prediction is wrong and fails, we must undo the incorrect speculative path and redirect execution to the right one. In VeeR EH1, we have two possible predictors, a basic one that always predicts branches as not taken, and an advanced one called G-share, which achieves a high hit rate and thus better performance. We can configure which predictor to use in the software, as we'll see in the examples. Finally, let's see how we can configure the various structures of the EH1. We can make hardware configurations before creating the bitstream or simulator binary, depending on what we're using. In this case, we can configure structures, size, enable or disable them, but we won't regenerate the bitstream or simulator binary, and we'll use the default configuration instead. However, we can also configure some structures via software. As seen in this table, we can enable or disable the branch predictor. If disabled, the prediction will always be not taken. We can disable pipelined execution, disable secondary ALUs, superscalar execution, and more using these two instructions. First, an instruction assigns a value to a register, which determines which structures are enabled or disabled. We then write this value to register 7F9, effectively enabling or disabling various structures. For example, having a 1 in the least significant bit disables pipelined execution. Also, having a 1 in bit 7 disables the secondary ALUs, and a 1 in bit 10 disables superscalar execution. In the exercises, we'll test different combinations and scenarios to analyze the programs.